Hello everyone, welcome to Startup Academy, your online gateway to, to success in the ISS examination. This academy aims only exclusively only for ISS exam. So in today's lecture, I will provide you with the basic concept of econometrics. As we all know that statistics third paper descriptive has three important subjects, which is sampling, econometrics, and miscellaneous. So we will be covering it by line by line. And the first topic we have taken today is econometrics from paper third, and we have taken the topic simple linear regression model. So what is simple linear regression model? Simple linear regression model is nothing but every word has its meaning. Simple means that the independent variable should be only one. Linear means that power of yi is equals to 1. Regression means that there should be error and we have to minimize error. And model, as you can see, the model is given by yi is equals to beta naught plus beta 1 xi plus epsilon I, where epsilon I is error, xi is independent variable, beta 1 is slope, beta naught is intercept, and yi is dependent variable. For all I goes from 1 to n. Now, before moving on for the derivation of this model, we will first know what are the assumptions that we have to make for this model to exist. So Gauss-Markov gave some of the assumptions which we have stated here. The first assumption is data should be randomly selected. Obviously, when we are talking about statistics, data is randomly selected and not selected on its own. That is, if it would have been the case, then it would have been the deterministic model and not statistical model. So here data is randomly selected. Second one is linearity. Because we are discussing simple linear regression model, then linearity is the assumption. That is, the power of yi or the dependent variable should be equal to 1. Then the third one is estimation of epsilon I, that is errors, should always be equal to 0, and variance of the error is a constant value which we have taken as sigma square, which this property is also known as homoscedasticity. And the fifth property is covariance of epsilon I and j is equals to 0 for all I not equals to j goes from 1 to n. This property is known as no autocorrelation. Covariance between two error terms should always be equal to 0. And the sixth property is there shouldn't be any multicollinearity. That is, the any of the two independent variables should not be intercorrelated with each other. If our model has these assumptions, satisfies these assumptions, then only our model exists and we can perform derivation on the model. So since we have taken these assumptions, then we can start deriving our model. So our model is yi is equals to beta naught plus beta 1 xi plus epsilon I for all I goes from 1 to n. So for derivation or the estimation of the model, we will take method of least square. So method of least square is given by E is equals to summation I goes from 1 to n epsilon I, where epsilon I is nothing but this error term. We will take the value from this, which becomes yi minus beta naught minus beta 1 xi whole square. Now we will take normal equations. Normal equations means we to estimate the parameter, first we will differentiate it with respect to beta naught and then with respect to beta 1, and then put it equal to 0 to get our estimator. So first we have differentiated it with respect to beta naught, we will get minus 2 summation I goes from 1 to n yi minus beta naught minus beta 1 xi. Next we will put this equal to 0. After putting it equal to 0 and taking summation inside, we will get summation I goes from 1 to n yi minus n beta naught minus beta 1 summation xi is equals to 0. Since we know that we are estimating for beta naught, we will take beta naught on one side and the rest others on the other side. And we will keep beta naught a single value, and we will divide whole of the equation by n. After dividing the equation by n, since we know that 1 upon n summation yi I goes from 1 to n is y bar, and 1 upon n summation xi I goes from 1 to n x bar is given by this. So we will replace these values here and we will get beta naught cap is equals to y bar minus beta 1 x bar. This becomes our equation number 1 and our estimator of beta naught. The next one is we will differentiate the equation with respect to beta 1, which gives us minus 2 summation I goes from 1 to n yi minus beta naught minus beta 1 xi into xi. And we will put again this equation equals to 0. By putting it equal to 0 and taking the beta 1 and taking the value of beta naught from equation 1, which we have calculated as y bar minus beta 1 x bar, we will take all the beta 1 terms on the other side and the rest of the term on the other side. So taking them on one side each, we will get this. We know that summation I goes from 1 to n xi is n x bar. So we have replaced here n x bar. Summation I goes from 1 to n. So after calculating this, we will get beta 1 cap as summation I goes from 1 to n yi minus y bar into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square, which is nothing but covariance of x and x comma y upon variance of x, which can also be written as sxy into sxx, which becomes our equation 2 or the estimator of beta 1. Now, what are the properties of beta 1 cap? Since we have found out the estimators of beta naught and beta 1, now we will discuss their properties. So, beta 1 cap can also be written as summation I goes from 1 to n yi minus y bar xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. This yi minus y bar can be separately written as this. Now, here we see that summation xi minus x bar is written alone, and we know that summation xi minus x bar is nothing but mean deviation, so it becomes 0. So this value, this whole value becomes 0. So beta 1 cap is left as summation I goes from 1 to n yi into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. So the first property that we have to check is linearity, whether our estimator is linear or not. So let us consider a value variable ki. Ki is equals to summation is equals to xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. So beta 1 cap becomes summation I goes from 1 to n ki into yi. Here the power of yi is 1. So beta 1 cap is linear estimator. Now the second thing that we will discuss is unbiasedness. What is taking the estimation of beta 1 cap? Then beta 1 cap can be written as summation I goes from 1 to n yi ki, and since ki and summation are treated as constant, they come outside and estimation of yi is written as this. Now we can write the value of yi as this. Here, beta naught, beta 1 and xi all are treated as constant, only estimation of epsilon I, which is the error term, is taken. Now by Gauss-Markov assumption, as we have discussed earlier, our estimation of epsilon I, which is error term, is always equals to 0. So our equation left is this. Now, since we will take summation ki inside, so we will get this equation. Now, discussing of summation ki. Summation ki is again summation xi ki. We will replace the values of ki and xi here, and we can write summation xi into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square plus 0, where 0 can be written as x bar into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. So this is, since this is the mean deviation, its value is 0. So we can replace this by this in that equation. And we know that summation of ki, summation I goes from 1 to n xi minus x bar is nothing but mean deviation. So it again becomes 0. So estimation of beta 1 cap is 0 plus beta 1 into summation I goes from 1 to n xi minus x bar whole square upon summation I goes from 1 to n xi minus x bar whole square. This numerator and denominator gets cut, and we get estimation of beta 1 cap as beta 1. That is, beta 1 cap is an unbiased estimator of beta 1. Now, variance of beta 1 cap. Variance of beta 1 cap again can be written as summation variance of summation I goes from 1 to n ki yi Now summation ki can be taken outside of the variance, which becomes summation ki square, and we are left with variance of yi. Now since variance of epsilon I is equals to constant is equals to sigma square, which is also equals to variance of yi. So we can take sigma square outside and we are left with summation of ki square. Now expanding the term ki, we will cut the numerator with the denominator and we are left with sigma square upon summation I goes from 1 to n xi minus x bar whole square, which is nothing but sigma square upon sxx. So this completes our property of beta naught, beta 1 cap. I hope you are getting till here. And moving on further, if you have any doubts, then you can write in the comment box. Only the relevant doubts will be answered by us. And moving on further with the properties of beta naught cap, similarly, as we have calculated the properties of beta naught cap, we will calculate the properties of beta 1 cap. So linearity, again, we can consider the power of y bar, or we can simply do it with like we did for beta 1 cap. We will take some, we will open this y bar and x bar, and we will take common terms outside, like 1 upon n summation I goes from 1 to n yi minus beta 1 cap xi. And here we see that power of yi is equals to 1. Hence, beta naught cap is a linear estimator. Now again, unbiasedness. Unbiasedness of beta naught cap is estimation of beta naught is equals to estimation of y bar minus beta 1 x bar, which is nothing but estimation of 1 upon n summation I goes from 1 to n yi minus beta 1 x bar. Now taking this summation here, estimation of 1 upon n summation I goes from 1 to n yi is nothing but taking the estimation inside, we will get estimation of yi. On opening the bracket, beta naught plus beta 1 xi plus epsilon I. And we know that estimation of epsilon I is equals to 0 by Gauss-Markov theorem. So we are left with beta naught plus beta 1 xi, which is nothing but we will take this summation inside, and we will get that 1 upon n into n beta naught, where n gets cancelled, plus 1 upon n beta 1 cap into summation xi square. 1 upon n into beta into summation xi square is nothing but beta 1 cap x bar. Now substituting this value here, we will get beta naught plus beta 1 x bar as the estimation of 1 upon n. So summation I goes from 1 to n yi minus beta 1 x bar. So these two gets cancelled because these are the equal terms with opposite signs, and hence we get estimation of beta naught cap is equals to beta. Hence beta naught cap is an unbiased estimator of beta naught. Now the third and the last property is variance of beta naught. We will write as variance of y bar minus beta 1 cap x bar. So opening the variances, we get variance of y bar plus x bar square variance of beta 1 cap minus 2x bar covariance of beta 1 cap into y bar. Covariance of beta 1 cap and y bar can be written as opening this beta 1 cap as summation I goes from 1 to n ki yi, and y bar as 1 upon n summation I goes from 1 to n yi. So taking out the common terms 1 upon n summation ki, we will get variance of yi. Now variance of yi, as we have discussed earlier, is nothing but sigma square. So sigma square upon n can come out of this summation, and summation of ki we all know that is nothing but mean deviation. Hence, variance of beta naught cap can be written as variance of y bar plus x bar square variance of beta 1 cap. Variance of y bar is sigma square upon n, and variance of beta 1 cap we have calculated earlier is sigma square upon sxx. Taking sigma square common, we will get sigma square into 1 upon n plus x bar square upon sxx as the variance of beta naught cap. Now we are about to discuss the one of the questions that came in 2020 in the ISS PYQ, and the solution we will discuss it in detail, which is based on this concept only. So the question states that we have been given a model yi is equals to alpha plus beta xi plus ui for all I goes from 1 to n, where x bar, which is the mean of x, is given as 0. We have to prove that covariance of alpha cap and beta cap is equals to 0, where ui, which is the error term, follows IID normal distribution with mean 0 and variance sigma square. So here also we'll use the method of least square as we have done earlier in the derivation. We have taken it as beta naught and beta 1. Here they have given us alpha and beta. And instead of epsilon I, they have given us mu I. The derivation goes similarly, only the parameters have changed. So taking least square estimator as summation I goes from 1 to n ui square, which is nothing but I goes from 1 to n yi minus alpha minus beta xi whole square. Now we will differentiate this equation firstly with respect to alpha and secondly with respect to beta to get the estimator of alpha and beta. So taking summation inside and dividing the whole equation by n, we will get alpha cap as y bar minus beta cap x bar. But since in the question we have been given that x bar is nothing but 0, so our alpha cap reduces to y bar. Now taking another normal equation, taking derivation of e with respect to beta, we will get minus 2 summation I goes from 1 to n yi minus alpha minus beta xi into xi equals to 0. Taking summation inside and multiplying as we did same in the beta 1 cap, we will get beta cap as summation I goes from 1 to n yi minus y bar upon into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. This is our equation number 2. So now we have to calculate the covariance between alpha cap and beta cap. We can again write beta cap as summation I goes from 1 to n ki yi, where ki is nothing but xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. So, and we also know that the summation of ki, which is summation I goes from 1 to n xi minus x bar, is nothing but 0 due to mean deviation. So, covariance of alpha cap into and beta cap is covariance of y bar, as we have done it in equation number 3, and covariance of summation I goes from 1 to n ki yi. Opening y bar 1 upon n summation I goes from 1 to n yi, and ki yi summation I goes from 1 to n ki yi. Taking the common terms outside 1 upon n summation I goes from 1 to n ki, we are left with variance of yi. Now variance of yi is again sigma square, so sigma square comes out of it, and sigma square upon n is into summation I goes from 1 to n ki. Again summation ki is nothing but mean deviation, so it will become 0. Hence covariance of alpha cap and beta cap is nothing but 0. Hence proved. This question was asked in 2020 in the ISS exam and it was of 15 marks. So if you have understood the topic clearly, then you can do this question within no time. And if you still have some doubts, then you can ask it in our comment section and genuine doubts will be answered. And I wish you all the best and start preparing for your exam now because it's high time now. If you liked our video, then you can like, share and subscribe, and if you didn't like, then you can also dislike and tell us in the comment what were we lacking at. Thank you.